Well, in the year of 1687, the most important question asked according to me is why do objects fall downwards? Why not any other question? Let's find out. I'm sure that you guys would have known that the falling of the apple or the ball was due to the natural phenomenon of gravity. But now, let's study the science behind gravity. Let's start by defining gravity. Gravity is nothing but a force between any two objects which pulls them together. Well, let's go back to the year 1687. It was in this year that Sir Isaac Newton published Principia, in which he hypothesized the inverse square law of universal gravitation. So, if F is the gravitational force acting between any two objects of mass m1 and m2, which are separated by a distance r, then F is directly proportional to the product of m1 and m2, and F is inversely proportional to r square. So, what does the equation of inverse square law of universal gravitation look like? Well, it looks like this. In the equation, you guys would have noticed the proportionality constant g. So what is this g? Well, it's a universal gravitational constant and it has a value this. The gravitational constant has a 10 raised to the power minus 11. So what does this tell us? It tells us that the gravitational force is very weak. So, of significant force to act between any two objects, either their masses have to be very high or the square of the distance between them has to be very less. So, now you guys might be wondering, why is it that when we have any two objects, for example two pens A and B, why doesn't the gravitational force pull them together? Why don't they stick together? Why is it that they stay apart? Think about that. Now, let's take up the two pens case again. So you have two pens A and B. Let them weigh approximately 30 grams and the distance between them is 0.3 meters. Now apply the universal gravitational formula. So what is the answer that you get? You get this. So, we just saw that the force of attraction between the two pens or between any two small objects was very less. In case of the pens, it was 6.67 into 10 raised to the power minus 11 newtons. Now, let's take the case of an object which has a very large mass, which will make a very big difference in the force of gravity. Let's take the example of the earth. Now, let's take the case of a man standing on the surface of the earth. Both the man and the earth have a specific mass. So, the man pulls up the earth, whereas the earth pulls the man downwards. So, when the man is walking or standing, why doesn't he just fly away or float away? Well, it's all because of the mass difference between the man and the earth. The earth has such great mass that the gravitational force exerted by the earth on the man is much greater than what the man exerts on the earth. If you use the inverse square law of universal gravitation and apply its formula to find the gravitational force exerted by the earth on the man, which is F equals g m1 m2 by r square, where m1 is the mass of the earth and m2 is the mass of the boy or the man, you will find it approximately equal to 4.8 into 10 power 8 newtons. This is a very large force that is exerted by the earth on the man. This is what keeps all the bodies or all the objects on the earth and doesn't let them float away. Now, let's talk about the acceleration due to the gravitational force of the earth, or also known as acceleration due to gravity. It is the acceleration produced in a body during free fall due to the gravity of the earth. Well, it's denoted by small g. Small g equals minus gm by r square. Why minus? Because it's in the negative direction or the downward direction. And why gm by r square? Well, it's only because of the gravitational field of the earth. So, we know that g equals minus gm by r square, where m is the mass of the earth and r is the radius of the earth. So we now know that the mass of the object does not affect its acceleration due to gravity. Thus, in a vacuum where there is no external factors acting, if you drop two balls, one of mass 10 kgs and the other of mass 1 kgs, both of them will hit the ground at the same time as they will accelerate at the same rate. So, now that you guys have a basic knowledge about acceleration due to gravity, let's talk about the variations in acceleration due to gravity. The variation in acceleration due to gravity are mainly due to height and depth. So, let's take up the case of height first. Here, I have this ball. As I didn't have a globe at home, so I think the ball would just do fine. Consider this ball to be the earth, and all the mass of the ball or the earth is concentrated at the center. Now we have to consider any object at a height h from the surface of the earth. So when is it at a height h, the distance of the object from the center of the earth increases. So we know that the acceleration due to gravity is given by gm by r square, where r square is the radius of the earth. So now we know that the radius of the earth is r and it's at a height h. So the new distance will be r plus h. So the new acceleration due to gravity at a height, let's take it as g naught. So g naught, which is the acceleration due to gravity at a height, will be gm by h plus r square, where m is the mass of the earth and h plus r is the total distance between the center of the earth and the height. So we found out g naught, which is gm by r plus h square, which is the acceleration due to gravity at a height h, and we know that g equals gm by r square, which is the acceleration due to gravity on the surface of the earth. So what happens when we take the ratio of g naught by g to get the fractional difference? Well, we get 1 plus h by r whole to the power minus 2. This tells us that the acceleration due to gravity at a height h is much smaller than the acceleration due to gravity on the surface of the earth. Thus, to conclude the first case, I would say that as you go higher and higher, the acceleration due to gravity decreases. Now, let's take the case 2, the case of depth. I'm sure that you guys will already assume that as you go deeper into the surface of the earth, your distance from the center of the earth keeps on decreasing, and thus the gravitational pull by the earth should go on increasing. Well, you guys are wrong. So, if you thought that if you go deeper and deeper into the surface of the earth, even the gravitational pull would go on increasing. But think it in this way. Suppose when you're halfway to the center of the earth, wouldn't the mass above you that's left behind pull you up also? And even if you apply the g equals gm by r square, here m won't be the original mass of the earth. So in this case, you have to consider the volume of the earth, where the density of the earth is considered to be uniform.
Well, let's now derive the formula for gravity at a depth. We know that the gravity at the surface of the earth is given by gm by r square. We also know that density equals mass by volume, thus mass equals density multiplied by volume. The volume of the earth here is 4 by 3 pi r cube, and the density is given by rho. Here, the density is taken as a constant or the density is taken to be uniform all over the earth. Now substituting the value of m in gm by r square, we get g at the surface of the earth as g multiplied by 4 by 3 multiplied by pi r rho. Similarly, if we do the same process for gravity at a depth, we get gravity at a depth equals g multiplied by 4 by 3 multiplied by pi multiplied by r minus d into rho. Here r minus d suggests that the radius of the earth has decreased as it's taken at a depth. By dividing g dash by g, we get g dash by g equals 1 minus d by r. This tells us that g decreases as we go down the earth.
Well, those were the cases of acceleration due to gravity at a height h and depth. Now, as the video is nearly coming to an end, we haven't still answered our most fundamental questions. Why does gravity even exist? Well, it's all because of space-time bending. So, in simple words, space-time bending says that any object that has mass bends space and time. So, for heavenly bodies, greater or more massive the bodies are, greater will be the space-time bending. All this leads to the pushing of the smaller objects towards the greater objects, and thus it's a simple explanation for how gravitational force came into existence. And if you want to know more about space-time bending, well, it's another great idea for another breakthrough challenge video.